Example 17.9 has a 20 kilogram slender rod, and at the instant shown it's got some omega, angular velocity of 5 radians per second, and wants us to find what alpha is, the angular acceleration, and what the vertical and horizontal components of force at the pin are. And I'll get into that in a second. And let's start out by making a free body diagram. We got this thin, slender rod. At O, these reactions they're talking about are some reaction at the tangential direction if we're talking about the direction it rotates about G. And we have some other force in the normal direction. And you should remember that from statics class. To finish off this free body diagram, let's put a mass times gravity there, and we were told that this initially has some 60 Newton meter moment applied to it also. Okay, let's go ahead and sum the forces in the normal direction. We get from last time that the acceleration can be written as omega squared and this distance r to g. Immediately we can calculate that. The force in the normal direction is 750 newtons. Okay, what about the forces in the tangential direction? It's going to equal, we learned last lecture, alpha rg. And what kind of forces do we have going in this case the y direction or the tangential direction? I have this tangential force at the pin. I have mg pointed down, and these are not the same. I should use different notation. And that's going to equal to our mass times alpha. This is what we were looking for. And we know the radius. If this is 3 meters right here, half of that would be 1.5 meters. Alright, now let's sum the moments about G. It's going to be equal to Ig alpha. The thin slender rod part is important because what is our I in this case? If you look at a thin slender rod that is rotating about the center, it's the easiest method or of least resistance. We get our I to be a 1/12 ml squared, and you can find that on the internet in the book. Just search for moments of inertia. Don't forget the alpha, and we need to calculate or sum up what moments we have. Well, there's this one at the pin right here, Ft, and it's acting a negative 1.5 meters away. And then we also have a negative 60 Newton meter moment that we cannot forget also. This one right here. Alright, from that we can get the forces in the tangential direction are 750 newtons. The normal direction is 19.05 newtons. And alpha is equal to 5.9 radians per second squared. There's our alpha, and that alpha is due to the moment applied and the moment applied by gravity. So check this out. It's in your book, but I recommend just trying it on your own. Sum the moments about O also. You can get the same exact answer. Yeah, I'll go ahead and do it for you. If I sum the moments about O, it's going to be equal to I about O alpha. So our I about O just changed. We still have the negative 60 Newton meters. That was the applied moment. 1.5 times the weight. was another moment. If we're looking about the moments about O, we have mg pointed down, we have this applied moment of 60 newtons. And all of that's going to be equal to I naught alpha. So if we look at I about O, if you went to your table in your book, we'd find it to be 1/3 ml squared. So I'm going to do 1/3 times 20 times 3 meters in this case, right? The full distance of the bar that the mass is distributed over, and then all of this is times alpha. You can also, so from this, the only thing we don't know is alpha, and we can also find it to be 5.9 radians per second squared. So that was a one equation problem, we just figured it out. You can also solve with kinetic moments. Take a look at that in your book. You get the same exact answer. Very similar to this one. I think it's knowing this method would be better than knowing all three, in my opinion.